and then we'll go from the slideshow, from current slide. Well, I thought we'd go from current slide. There we go. All right, and here comes Anaya. So let me get her in. Whoops, I put that in the wrong place. Anaya's here. Okay. Now, I've still got a little bit of housekeeping to do. First, I'm going to push Weston over to the right a little bit, and everybody else who's lined up there. And let's move this toolbar out of the, so I can see the slide better. And I think we're just about ready to go. So first, let me ask, any questions, issues, concerns, problems? Anybody? I take it not. I'm hearing no response. Let me tell you just a few things. I may have mentioned these on Tuesday, but a few things are new. Oops, here comes Brianna. Let me get her in here. Nope, right there. All right. All right. So, I guess first, sort of functionally, I hope I mentioned this last time. If I didn't, let me say it now. My office hours have changed now. We're now in the second half of the term. I lost my first mini-term class and picking up the second mini-term class. Now the difference is the second one starts later. So whereas on Tuesday and Thursday before, the only office hours I had were from 8 to 8:30 in the morning. That was it, because I was in class the rest of the day from 8:30 until 5:45 with just 2 15-minute breaks and 1 30-minute break when I tried to cram down as much lunch as I could. Oh, Brianna must not could have gotten in too well, because she's coming back in. I've got her marked. Okay. But the second mini-term class starts at 3:15 and goes till 7:45 in the evening, which means now I have some office hours on Tuesday and Thursday afternoon, and I just put them down there approximately 1 to 5. Okay, I actually get out of my last class at 12:45, and then I start the next one at 3:15. But I also eat lunch some time in there too, but I'll, if someone's there, I can adjust my lunch. So I just put down 1 to 5. And I put it on the, about 3 places in Blackboard. At the very beginning, when it has instructor contact information, preferred office hours, I put them there. Best times to reach, I put them there. And then I also, on the week 9 handouts, I changed and went to the new locator card. So it's there on the locator card. So those 3 changes I've made. So I do have those office hours listed now. Tuesday, Thursday, 1 to 3. Okay. Now, okay. The next one, I think, is going to affect this class, but I don't know for sure that it will. Okay, I'm going to try to do this without taking too much class time, but I always take too long. I had an appointment with my hematologist on Tuesday, so that meant last Friday I had to go to get blood work done, so he would be able to see what my counts were. I knew my counts would probably be high and I'd probably need a treatment. Well, actually I saw the counts too, because they put them on the portal before I actually saw him. And yeah, my white cells counts are really high, so I need a treatment. But the bad news is, that's not good news either, but the other part of it is my red cells are really low. My platelets are really low. My hematocrits are really low. My hemoglobin is really low. The other things that I would have hoped been sort of stable, except that the white cells are sort of crowding out the others. So when he saw that, he said, we need to do some more blood work so we can tell make sure that the treatment where I'm going to give you is going to be the best treatment for you, and to make sure there's nothing else going on, causing something else. So I had to go in yesterday morning to get more blood drawn, and got that done, and I should get the results probably tomorrow, because he said it'd be about 48 hours. Okay. Could happen sooner, but probably won't be until tomorrow sometime. And here comes two people waiting. This is Briantra and D, so let me let those in and get them marked here. Briantra is here, and D is here. Good deal. All right. Up to 15 students, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I actually have 16. I hope I haven't marked someone twice. I think somebody has, I don't know. I'm not going to worry about it now, though. Okay. Now, what's the bottom line for all this? What he said in the thing, if I am going to have the same treatment I had, which has been really effective lately, except it also knocks out my red blood cells and platelets, and they're already starting low, so that's why he's a bit concerned. Because it's been more than 9 months since I had my last treatment, they want to start me slow on this again, even though I've had it several times before, but it has been a while, so they're going to do 10% one day, 90% the next day. Well, generally I have my treatments on Fridays when I don't have any classes. Well, I can't do that on 2 back-to-back days, so that means it's going to have to be Thursday and Friday. So my anticipation is, but it hasn't been scheduled yet, so I don't know, it could be that next Thursday that may affect this class. It may not, okay? That could be they can't schedule me for Thursday and Friday of next week. They may be full up in the transfusion lab. Or it could be that they're full up in the morning, and here comes Ashford. Let me let him in here. There he is. So Ashford is here. And they may have to get me later in the day on Tuesday. I don't know. So anyway, on Thursday. It could be that, it probably will be, one of these Thursdays coming up, probably fairly soon, I'm probably going to have a treatment on a Thursday. If it's in the morning, it'll maybe affect this class. Okay, somebody I think has a microphone on. Okay. Ashford, I think your microphone's on. Or D, maybe it's yours. D? All right. D, I think your microphone's on. All right, good. Okay. If you have something to say to me, leave it at home, but it sounded like it was just background noise. So that is probably going to happen. It may or may not affect this class. Okay. But then it will affect the next Friday. I'll have 0 office hours on that Friday, because that 90% treatment is probably going to take most of the day. So I'll probably be there early, and it goes most of the day. So that's that. Now, on top of all this happening, this is completely personal, but it still may in fact impact the class, so I just want to let you know. One of my very best friends in Birmingham collapsed, I think it was Tuesday evening, was sent to the emergency room, and she's in intensive care now and on life support, and they don't think she's going to make it. So I'm her, she doesn't have any family any closer than a really old sister in Virginia, so I'm her contact person here. So it may be that I could be drawn away having to deal with some of that kind of stuff at any time. Hopefully I can work around it and do it on Fridays and weekends and times when I'm not in class. But if something does come up that I have to take care of, that could happen too. So anyway, this has not been one of the best weeks ever. So anyway, let's get going. Have you got any issues, problems, concerns, anything you want to bring before the class? Mostly dealing with math. Yeah. Any? Okay, I thought I heard something, but then it went away. All right, well then let me minimize this and get started where we left off before. Okay, we're trying to finish up chapter 1, okay? Functions in the graph, and 1.9, if it would advance, but it won't. 1.9 is dealing with inverse functions. Now, I thought we got started with this last time, but I can't find a mark on the page, so it may have been we just ended at 1.8. So, here are our objectives in this section. Find the inverse function informally. Now, they do this. To me, it's almost sort of a waste of time, but these people are supposed to be professionals. So I'll try to move through this fairly quickly and verify that the two functions are inverses of each other. That is important, so we will be doing that. Use graphs of functions to determine whether functions have inverse functions, and we'll go into that. We haven't hit that yet. That includes the horizontal line test. Now, earlier we had the vertical line test to determine if a relation is a function. Now we use a horizontal line test to determine whether the function is one-to-one, okay? You have to be a one-to-one function in order to have an inverse. And then, finally, we'll hit the really important part, finding inverse functions algebraically, okay? So that's what the plan of attack is, so let's go for it. Let's first talk about what in the world are inverse functions. Now, way back in your past, after you learn to count and that kind of stuff, shortly after that, probably in grammar school or something, you started learning to add, okay? Now, addition was an operation, and you probably went through and were memorizing all these addition tables and flashcards or whatever you used to help do that, and you thought, wow, finally I've got that done. And then all of a sudden they turned around and had you start subtracting. Well, what did subtraction do? It undid addition. Addition undoes subtraction. They are inverse functions of each other. So guess what? You've been dealing with inverse functions ever since you've been in math, period. Okay? Then sometime later, you got into the multiplication tables. You thought you finally got through with addition, subtraction, and then they sprung this multiplication stuff on you. And you had to memorize all those multiplication tables and things like this, maybe flashcards again. I don't know. That's what they used when I was in school. That was a long time ago. And then finally, I think I got this down, and then they sprung division on you. What did division do? It undid multiplication. And multiplication undid division. Well, guess what? They were inverse functions of each other, so you were dealing with it again. Sometimes, probably much later, you got around to raising functions to power, or raising numbers to powers, like 3 squared, 4 squared, maybe even cubes. Well, you got that down. You're more used to stuff now. It wasn't as scary, but at some point, then you started taking square roots and cube roots, which undid the squaring functions and the cubing functions. And you can have any roots you have for any power you have. Okay? Those were inverse functions of each other. Okay? So you have been doing this your whole life in mathematics. You've been dealing with inverse functions. Now we're going to be dealing with inverses of combinations of functions. In fact, you weren't even calling them functions then. They were inverse operations, okay? Now we're going to deal with inverse functions. We finally got down what a function was. Now we're going to undo it with an inverse function, okay? So one way that we can represent a function is a set of ordered pairs. Remember that way back at the beginning of this chapter? For instance, oh, here comes Terrell, okay? Let me find my pen and my roll sheet and get Terrell marked present. Okay, good deal. Well, I thought oh, and here comes Shamari, I believe it is. She's been PC, so hopefully she still is PC. Okay. So let me just check and make sure. Shamari, you're still PC, right? Okay, good. I thought that was you. Okay. We're talking about inverse functions, and we're talking about, and by the way, we're in Chapter 1, Functions in the Graphs. 1.9 is inverse functions, and we're on page 84, very beginning of the section. We were talking about that early on when we were doing functions, way back in 1.4, seems a long time ago. We were several ways to express functions, and one of them was a set of ordered pairs, okay? Ordered pairs was one number comma another number in parentheses, ordered pairs. So here's a function written as an algebraic function. F of x is equal to x plus 4. Pretty simple function, linear function, okay? You don't need to know this, but the slope is 1, the y-intercept is 4, so we know that, okay? But we can represent that function, or at least a little bit of that function, if our domain is not all real numbers, like it would be for this in general, but our domain is only these 4 numbers, 1, 2, 3, and 4. Well, we can just put 1 in here. 1 plus 4 is 5. 2 plus 4 is 6. 3 plus 4 is 7. And 4 plus 4 is 8. So that would be the range. So that function takes you from the domain A, 1, 2, 3, 4, to the set B, which is a range, 5, 6, 7, 8. This is a pretty simple function, right? Now, writing that little function as a set of ordered pairs, since this is all your domain right here, and anytime you have a finite domain, especially if it's a fairly small finite domain, you can write it as a set of ordered pairs. So here's the function f of x equal x plus 4. It can be represented as the set of the ordered pairs 1, 5, 2, 6, 3, 7, and 4, 8. That's it. That's all the domain, 1, 2, 3, 4, 5, 1, 2, 3, 4, and all of your range 4, 5, 6, 7, 8. Okay? Now, in this case, what you could do, this is a new operation here, interchange the first and second coordinates, okay? Just flip them, okay? And you form the inverse function of f, which we'll denote by f inverse. Now that's f with a superscripted -1, okay? Now, time out for a moment. In the past, if you had a number with a superscript -1, like 4 to the -1 would be 1 over 4. Okay, that's not what a function to the -1 means. If you had a variable x to the -1, that meant 1 over x. Okay, that was an multiplicative inverse. Okay, it was an inverse, but it was a multiplicative inverse. When you have a function raised to that, that does not mean reciprocal. Does not. This means the inverse function. That means you're exchanging your inputs and outputs. That's what it means. Okay? Now, I can't get this to advance. All right. That new function is also a function, but now you're going from set B, which was this set, to set A, because now you're plotting the other way. Okay? And you can write that inverse function as, and here they just gave it to you, Before, okay, and this was a pretty simple one, I'm sorry. Before, it was x plus 4. Now when you're going from 5 to 1, from 6 to 2, from 7 to 3, and from 8 to 4, you're subtracting 4. So the new function, the inverse function, is then x minus 4. And that plots from set B, 5 goes to 1, because 5 minus 4 is 1. 6 goes to 2, because 6 minus 4 is 2. 7 goes to 3, because 7 minus 4 is 3. 8 goes to 4, because 8 minus 4 is 4. Okay? Notice all you did was flip the input and the output, and it had a new function that did that. That's the inverse function. Note that what was the domain of f is now the range of this f inverse. And what was the range of f is now the domain of this f inverse. Now, that's one way to represent a function, is set of ordered pairs. Another way is to think of it as a mapping, okay? And that's what this is doing. Here you start with some value, x. In our case, that was 1, 2, 3, and 4. That's the domain of your first function, f, okay? Map that onto f inverse. That's the range. And that gave you 5, 6, 7, and 8 over here. Well, the f, okay, the inverse function takes from here and maps right back to there. So what do you wind up with? The same x you started with. Here, f takes this x and becomes f of x. F inverse of x takes that output, f of x, and plots it back to being x again. So this is indicating domain of one becomes the range of the other, and vice versa. And like I was saying before, the functions f and f inverse have the effect of undoing one another. Okay. Now, in other words, when you form the composition, okay, whoa, here we go with the composition now, of f with f inverse, okay, what is happening? You compose f of f inverse, you wind up back where you started from, okay, x, okay. You obtain the identity function. And guess what? When you do f inverse of f, so do f inverse of f, you wind up back at x again there too. And remember before we said that compositions usually don't go both ways. But I paused and put a caveat in there, but when they do, they're very special functions. And these are those special functions. When a function is an inverse of each other, you can do f of f inverse, you're going to get x, and you do f inverse of f, you'll get the same value x. Okay? Now, the only little difference here is the x's here are the input for your f inverse, which are the output for your f, okay, of course. So these x's in the previous example could only be 5, 6, 7, and 8, okay. However, this x is the input for f, which is the output for f inverse, and that would be 1, 2, 3, and 4. So even though they're the same x's here, they may represent different sets, okay. Now, if both of them are all real numbers, then they're the same set, okay. So here's example 1, bottom of page 84. Find the inverse of f of x equal to 4x. What would be your guess? Just make a guess here. What function would undo, I'm going to give you a hint here, multiplying 4 times x? What would be your guess of f inverse? Say that again. Okay, not a power. What undoes a multiplication? A division. that would be x divided by 4. Okay? Now, it says then verify that both f of f inverse and f inverse of f are equal to the identity function. So let's do the first one here. Let's do, if I can get my dogs downstairs barking like crazy, that means the neighbor's cat is over there teasing her. Cat sits outside the door and just sits there and lets the dog bark at her, and it doesn't care. They're a mess. So we're trying to try f of f inverse, this thing right here. What is f inverse, or at least our guess, is x over 4. So let's just put in x over 4. Okay. Now the f function takes whatever's inside the parentheses and multiplies 4 by it. So that would be 4 times x divided by 4. Hey, look at that. The 4's divide away and you wind up with x. So that one worked. Okay. Let's do the other one. This one we're going to do f inverse of f. This is the composite, remember? Okay, well that would be f inverse of f was 4x. Well, what does the inverse function do? It takes what's in the parentheses and divides by 4. So that would be 4x, that's what's in the parentheses, divided by 4, and guess what? Bing, 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 that's also x. Yes, good choice. The division function, x divided by 4, undoes the multiplication function, 4 times x. They are inverse functions of each other, and we just verified it, showing that f of f inverse and f inverse of f both produce the identity function, which is just x. Okay, so good deal. Let me erase my scratch. Any questions on that? Oh, is this somebody new coming in? Let me see. No, I don't see anyone. We should have 16 people here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we've had some people show up and then disappear, which that's their choice, I guess, but it seems like they're missing some math here. All right. So let me clear my screen here if I can get the things to show up down here. Now they're not popping up today. Well, that's not good. I just had figured out how to clear the screen. Ah, there it is. Whew. Okay. We'll erase that ink and see what they do. The function f multiplies each input by 4. To undo that, you need to divide each input by 4, which would mean f inverse, at least our first guess would be x divided by 4. If f of x is 4x, f inverse would be x divided by 4. Okay, to verify this is true, we're first going to do f of f inverse. Well, f inverse we just said was x divided by 4. The f function takes whatever's in the parentheses, in this case it's x divided by 4, and multiplies x by it, 4 by it. So that's 4 times x over 4, which is, yes, x. Okay, but to do it the other way, we're going to do f inverse of f. F inverse of f. F of x is 4x, remember from the very beginning. The f inverse function takes whatever's in the parentheses and divides by 4, and sure enough, that's 4x over 4, which gives you x again. So yes, we've got both of those to verify. All right, good deal. That was a very simple one, okay? Understood. Here's your definition of an inverse function. This is on the top of page 85. So let's say that f and g are both functions, okay, such that f of g of x happens to be x for every x in the domain of g. Now that's where this x began, in the domain of g, okay, and then when you operated on it with g, you got a value that was in the range of g that had to be in the domain of f. If it was, then when f operated on it, it got you back to that same x again. Okay, but also when you do g of f of x, okay, now the x starts off in the domain of f, which may have been different from this x up here. And when you operate it with f, you get it into the range of f. That needs to be in the domain of g, and if it is, when you operate it on with g, it takes you right back to that original x again. Okay, so if these two things happen under those conditions, the function g is the inverse function of the function f, because g undoes f and f undoes g. The function g is denoted by f inverse, f to the minus 1, which doesn't mean reciprocal. It means inverse. When you do it to an inverse, to a function, that means inverse. So that's read f inverse. So f of f inverse is x, just like we saw before, and f inverse of f is also x. The domain of f, the original function here, must be equal to the range of f inverse. Has to be. And the range of f inverse must be equal to the domain of f. Did I say that wrong? The range of f must be equal to the domain of f inverse. Okay. Now, and here's what I've been preaching all along. Do not be confused by the use of the superscript -1 to denote the inverse function. In this text, and in most math books, whenever a function says to the -1, has that superscript of -1, it always refers to the inverse function, not to the reciprocal. A number to the -1 is a reciprocal. That's a multiplicative inverse. A variable to the -1 is a reciprocal, which is a multiplicative inverse. A function to the -1 is not a reciprocal, it's the inverse function. Okay? If the function g is the inverse function of the function f, then it must also be true the function f is the inverse function of g. Has to be, always. For that reason, you can say that the functions f and g are inverse functions of each other. Okay, so it doesn't matter which way you do f of g or g of f, you're going to get the same result. Okay, now they're skipping example 2. Okay, so let's do example 2. Let's go back a slide and pull up our favorite old whiteboard, which means I'm going to have to do a little more adjusting of my screen here. You can't see this, but I have a toolbar that for some reason they plant in the white space, so I can't write there. And because I have a list of you folks over here on the right hand side, you can't see, that's covering part of my white space. So I take the whiteboard and move it as far to the left as I can, and you probably can't see me do this at all. You just see white space and say, he's not doing anything, but in reality I am on my screen. And if you watch one of the recordings, you'll see that happening. Okay, which of the functions is the inverse function of f of x? So here's our f of x. Let me get the book in my lap so I can read it better. So here's our function f of x. This is not quite as simple as we had a while ago. This is 5 over x minus 2. Now notice they're not asking you to try to guess what the inverse function is. Ugh. It would take a lot of guesses, and we may not get there for a while. Okay? But they're giving you two choices of what could be the inverse function. Is it g? And g of x is x minus 2 over 5. Or is it h? And h is, boy, fairly complicated looking, 5 over x plus 2. Okay. Now, most of the time they're not going to be so generous to you. They're saying, well, they're not really saying, well, are they? Well, they're implying that one of these is the inverse. main way, I would say the only way we can check, is to test them. And what's the test? Do f of g of x. Compose the two functions with each other, see what you get. Will that be f compose with, plug in what g of x is, x minus 2 over 5. And now you see where it gets a little more complicated. What does the f function do? The f function starts with the number 5 in the numerator, okay? Then draws a line, and then puts whatever's in the parentheses here next. What's in the parentheses here is x minus 2 over 5, and then subtracts 2 from that. All right, that's sort of a pain in the neck looking thing. What this is called in some text, I think back in your pre-calculus algebra, you called this, or maybe it was intermediate algebra, you called this a complex fraction. I really don't like the name complex fraction, though it certainly is complex. I would say a complicated fraction, because you have a denominator in your denominator. You have various things. So how you go about simplifying this is find the least common denominator of all your denominators. Well, that's only 5. That's the only denominator you have. Take that 5 and multiply the numerator by 5 and the denominator by 5. This entire denominator multiply by 5. Well, that numerator becomes 25. Okay, because 5 over 5 is 1, and you can multiply by 1 anytime you want to. Doesn't change the value. When you multiply 5, distribute 5 to this first term, you wind up with an x minus 2, because that 5 and that 5 cancel out. Then when you multiply by the next term, you get a minus 10. Okay, well, what does this give you? This gives you 25 over x minus 12. I can't get my pen to write. Hey folks, that's not x. I can't make it become an x. So that doesn't look like that's reciprocal. So we're going to say not reciprocal, inverse function. We'll say not. Okay? Let's try the other one. F of h of x. Let's see what we get when we do that one. Oh boy, this looks like a real pill. That would be f of 5 over x plus 2. This takes us way back. What does the f function do? It starts with a 5. And it divides by what's in the parentheses, which in this case is a 5 over x plus 2, and then it subtracts 2 from that. Ooh. Well, these parentheses really aren't doing anything for us except showing that that's what the x was here, so we took them in. So I'm going to erase those parentheses if I can get my eraser to work. Yesterday in a class it just stopped working. Okay, so I'm going to get rid of those for now. They weren't really helping anything. And looky here, 2 minus 2 adds to 0. So that gives us a 5 over 5 over x. Now I could do what I did before and multiply numerator and denominator by x. That would certainly work. But you know, this is a simple division problem. This is 5 divided by, that's supposed to be a divided by. Why in the world the pen chose to do that, I do not know. I have to slow down my writing, and when I slow down my writing, then it won't write. Divided by, okay. Oh, here comes Ivan. Hold on a moment, folks. Let me get Ivan marked present. Yuck. I'm getting my cords tangled up. Ivan is right there. All right, turned out being a pretty good attending class today. Hopefully some more people will still keep coming in. Okay. So this is Ivan. We're on in chapter 1, of course, functions in the graphs, section 1.9, which is the last section we're going to do in this, inverse functions. We're on page 85 doing example 2, which is not on the PowerPoint, and that's what we're doing here. We got it down to the case. So the question is, here's a function f, and there's two functions g and h. We're asking if either of these is the inverse function of f. Now, you've missed the first part, but let me explain. If it's an inverse, then when you do compose one function with this inverse, you're going to wind up with the identity function. Well, we composed f with g, and we got something that definitely is not an identity function. So now we're doing f with h, and that's showing a little more promise, and that's what we've done down here, f composed with h. Okay, now we got to this point, and rather than multiplying numerator and denominator by x, I decided let's just go and do a division. That would be 5 divided by 5 over x. Well, if you remember, when you did division of fractions, that's the same as 5 times the reciprocal. This is a reciprocal, x over 5. And look at what happens. The 5's go away, and you're left with x. That's the indication h may be the inverse function. Certainly not g. Let's check it the other way. Let's do h of f of x. Remember we did composite functions before. That would be h of, what was your f of x? 5 over x minus 2. Okay. Well, the h function starts with a 5 and divides it by whatever's in the parentheses. What's in the parentheses here is 5 over x minus 2. Okay, it takes that and then adds 2 to it. All right, well, for this first part, I'm going to do exactly what we did before. I'm going to come up here and do this. I'm going to do 5 divided by 5 over x minus 2, which is 5 times x minus 2 over 5, and look at what happens. The 5's go out. This gives you x minus 2. And then with that, okay, Rosa, are you needing something? Your name keeps popping up. I don't know why that was happening, but it was. I've never seen that happen before. Were you trying to contact me? All right, Tamia, I think was here before. She's back. Okay, I think she was having trouble getting in before. Yeah, so she was one of the ones we lost, so hopefully she's back in full force again. So this 5 over x minus 2 just becomes x minus 2. Then we add 2 together, and look what happens. Minus 2 plus 2 is 0. We wound up with x again. The identity function, yes, h is the inverse of f. Now, all that mess that they had at the beginning of, where in the world is my pen? There it is. Okay, these are inverses of each other, f of x and h of x. And this doing it by inspection, no way you were going to get that by inspection. Only way we got it is they gave it to us. Okay. Oh, and by the way, each of these examples is followed by a checkpoint. Please do your checkpoints. Okay, are there any questions about inverse functions so far? Okay, if not, let's go back to our PowerPoint And let's see, we should have 18 students here. I don't, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I have 20, so evidently we have lost a few. So let's go back to 1.9 and we'll resume the slideshow. They've changed this. Okay. The graph of inverse functions. This is the top of page 86. Okay. The graphs of a function f and its inverse, f inverse, are related to each other in the following way. And remember, at the very beginning, we said if a point AB is a point lying on the graph of f, in other words, you go over A on the x-axis, go up B on the y-axis, that's on the function f. Well, that means that the point BA, remember when we reverse the order, that's inverse, if you go over on the x-axis B and go up A units, you're on the graph of f inverse, and vice versa, okay? That means that the graph of f inverse is a reflection of the graph of f along that identity function. There's the identity function showing up again. And this is what it means. If here is your f function, okay, this little bluish line here that goes up like this, later we'll talk about what's required for that, then your f inverse is going to be like this. Everything is mirrored across the diagonal there, which is y is equal to x. AB, when you come over A units on the x-axis, go up B units on the y, that's on your f of x. That means if you go, get out of the way there, go over B units on the x and go up A units, that's going to be on your f inverse. So they're all mirrored across the identity function. Y is equal to f. The y is equal to x. Okay? Any questions? Now, if you were to ponder that for a while, okay, we're going to stop and not ponder yet. We're going to get there in a minute. Let's do example 3. Sketch the graphs of the inverse function f of x equal 2x minus 3. Okay, I think I can sketch that if I can get my pen to show up. Oh, there you are. Okay. We'll do a vertical axis here and a horizontal axis here. We'll tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8. That doesn't mean you make them mad. That means you just make tick marks where they are. And I don't draw these very evenly. Just get over it. Okay. And we'll go up 1, 2, 3, 4, and down 1, 2, 3, and 4. Kind of wish I wasn't using red, but that's okay. All right, so let's do this one first. We know it has a y-intercept. If I can get the pen to show up, there it is. Y-intercept of minus 3, so that's down here somewhere. Okay, and it has a slope of 2. So meaning it goes up 2 for every 1 it goes over, up 2 for every 1 it goes over, up 2 for every 1 it goes over. I'm running out of room there. It goes down 2 for every 1 it goes to the left, and we're running out of room. So there it is. That's a linear function. A straight line does something like that. Okay. Now, they're telling you that the inverse function, f inverse for that function, is 1/2 of x plus 3. Now, that's not intuitively obvious, and if we were really cynics, we would have to verify it. We don't have time to be cynics, so let's just take their word for it. Now, that's not going to be quite as easy to graph, except if you do it smartly. So let's first take x equal minus 3. Why not minus 3? So if x is minus 3 plus 3 is 0, half of 0 is 0. So we got minus 3 on the x, 0 on the y. So there's one. Oh, let me do a different color. can you pick me out a color? I've got black, dark red, orange, yellow, green, dark green, light blue, middle blue, dark blue, purple. Give me a color. Not red. I'd say not even dark red. Blue. You want the light blue, middle blue, or the dark blue? Dark blue. Okay. I usually call the light blue Carolina blue. But okay, so that's going to be this one. I'm doing this one in blue. I did that one in red. Okay. So that worked well. Let's pick another X. Well, I want an X that when I add these two together, I'm going to get an even number so I can divide it out. Is that okay? So how about X equal 1? 1 plus 3 is 4. Half of 4 is 2. So when X is 1, Y is 2. Okay, it's somewhere right there. Okay. Let's pick another one. That works so well. X equal 3. 3 plus 3 is 6. Half of 3 is 3. So when X equal, what did I say, 3, then you had Y is equal to 3. Hey, looks like that point right there. Get out of there. Okay, it looks like that may be the same point. Let's go back here. It looks like there should be one in here, like minus 1. Minus 1 plus 3 would be 2. Half of 2 is 1. Sure enough, that worked well. Okay, it looks like this is something with a slope of 1/2. That means it goes up 1 for every 2 over, up 1 for every 2 over, up 1 for every 2 over, up 1 more for every 2 over, somewhere about in here, and it would go down 1 for every 2 to the left, down 1 more for every 2 to the left. And it looks like we're running out of room, so here would be that line. I don't draw straight lines very well. Okay, now I need another color, folks. Either black or orange or yellow or green or purple. Give me a color. Anyone? Purple. Okay, we'll use purple. Now, unfortunately, that's sort of similar to the blue, but I think we can tell a difference. What I'm going to do is my identity function. That's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, running out of room there, minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, minus 4, minus 4, minus, yeah, we get the idea. And let's see if we can, well, in fact, I want to leave it a dotted line like that. I don't need a solid line. Okay, well, guess what? The function f reflects across the identity function and gives you your inverse. Yeah, that worked. Now, a couple of things I want to point out to you. I'm going to go back a slide, and let's look at this. Now, I'm jumping the gun on you. Notice something about the f function here. Okay, if I could get my pen, there it is. The f function, notice here, it's always increasing. Well, guess what the f inverse? It's also always increasing. Let's go back here. Your f function here was the red line. If I could get it to show it, there it is. That's always increasing. Your f inverse is always increasing. Interesting. Is that always the case, or did it just happen to be in these two cases? We'll see that in a minute. Let's first see how they did their problem. We'll erase all mine. And what they did here, oh, there it is. There's the graph of f. They did it real quickly, didn't they? They did ordered pairs. They did a little further than we did. We did 0 minus 3. We did 1 minus 1, 2, 1, 3, 3. We may have even done 4, 5. I guess that one was, okay. Whatever that was, we may have done that. What they did, cheats that they are, they just reversed the order. They did minus 1, minus 5, minus 1, minus 3, 0, 1 minus 1, negative 1, 1, 1, 2, 3, 3 was the same, and on up if they'd gone. Hey, that looks pretty close to what we did. That's why I said I wish I had reserved my red line to be my one-to-one function and drawn the other two lines something else, but it's okay. It appears that the graphs are indeed reflections of each other across the line y is equal to x, which there it is, that line right there. Okay. You can further verify this reflective property by testing a few points on each graph. Yeah, I mean, and look at that. All of them are what you do, these points, they just flip over one from another. Flop the x and y coordinates. Okay. Now, note that in the following list that if point AB, that's A for x, B for y, is on the graph of f, then every time B comma A, x equal b, y is equal a, is on the graph of f inverse. And I pointed that out to you, and sure enough they were. And here you see them again. You saw them on the graph, and you see them here. If negative 1, negative 5 is on f, negative 5, negative 1 has got to be on its inverse. If 0, negative 3 is on f, negative 3, 0 is on y, on f inverse. 1, negative 1 on f, negative 1, 1 is on f inverse. 2, 1 on f, 1, 2 on this. 3, 3, 3, 3, and you keep on going. 4, this would be 4, 5 here. That would be 5, 4 there. Keep on going. Okay? I think I pointed that out to you. Now we get to a test. Not a test that you're going to take, but how do you determine if a function has an inverse? We got to introduce this new concept of one-to-one functions. Okay? And here's what we mean by that. That reflective property of the graphs of inverse functions gives you a geometric test for determining whether a function has an inverse or not. That test is the horizontal line test for inverse functions. Here's what it is. A function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. Now, I already had a vertical line test. It's a function if, not a one-to-one, but a function if no vertical line intersects that graph more than once. To have an inverse, now you add the other thing that no horizontal line can intersect that function. And let's go back and look. Those two we looked at. There, notice your f function here. Okay, it passes the horizontal line test all the way. The f inverse, it passes the horizontal line test all the way. Now, it looks like this is beginning to be very close to a zero slope, but as long as that does, who cares? On this part of the domain, it has an inverse, and on this part of the domain, that has an inverse because it's one-to-one. It passes both the vertical line test and the horizontal line test. Let's look at this one. Sure enough, both of these functions, f function here, passes the horizontal line test. It's a straight line, and so does f inverse. So they both pass the horizontal line test. Okay. If no horizontal lines intersect the graph of f at more than one point, then no y value is matched with more than one x value. That is a central characteristic of what we call a one-to-one function. Before we had, for any given x, could only be one y. Now we say not only that, but for every y, there can only be one x. Okay? That's a stricter kind of function than just a regular function. It's a one-to-one function. So a function f is one-to-one when each value of the dependent variable, the y usually, corresponds to exactly one value of the independent variable, usually x. A function f has an inverse inverse function if and only if f is 1 to 1. If f backs up on itself, it cannot be 1 to 1. It fails a horizontal line test, it cannot have an inverse. Okay? So here are a couple functions. Here's a function. F of x is equal to x squared. The table on the left is a table of the values of f of x equal to x squared. You plug in a minus 2, you get a 4. Square it, you get a minus 4. Plug in a minus 1, square it, you get a 1. Plug in a 0, you square it, you get a 0. Plug in a 1, you square it, you get a 1. 2, square it, you get a 4. 3, you square it, you get a 9. Okay, that's a function. It passes the vertical line test. However, the table on the right is the same table, but we have flipped the values to see if it's an inverse function. Well, guess what? When you flip these two, and those two, and these two, and these two, and these two, we flipped them all. Look at this. Here you have an input here, the same as an input here, with a different output. This one here is not a function. Okay? Where did my pen go? There it is. This one's not a function. I'm still in purple. Okay? That is a function. This one's not. So therefore, f of x equal x squared does not have an inverse. At least not in its whole domain. Okay? And here's where we'll be talking about something a little bit differently. So let's move on to here. The table on the right does not represent a function because the input 4, for instance, just one of them, is matched to two different outputs. Okay, x equal minus 2 or x equal 2. Same thing happened with 1. 1 could be plus 1 or minus 1. If you look at that, see here's a plus 1 with a 1. Here's a plus 1 with a minus 1, plus 1 with plus 1. Not a function. Okay, so it's not just the 4, it's several of them. Okay, so f of x is equal to x squared, not 1 to 1, does not have an inverse function. You might say, oh, but you could take a square root. Well, no, you can't. When you take a square root, you have to do plus or minus, not a function anymore. Now, there is something you can do. I'll wait just a moment. Okay? No, I'm not going to wait a moment. I thought they would graph this for you. Here's what it looks like. The function looks like this. I'm still in the purple. If you only took as your domain from minus infinity to 0, that is 1 to 1. It passes the horizontal line test. Or if you took as your domain 0 to infinity, then that's 1 to 1. So these two, f of x equal this on that domain, and f of x equal x squared on this domain, yes, both of those are 1 to 1. They do have inverses. This one over here would be the positive square root of x. This one over here would be the minus square root of x. And like I said, when you take the square root of both sides, you get plus or minus x. Well, if you only took the square root of one side, this gives you minus x, that gives you plus x. Okay? So, sure enough, if you restrict your domain, it can be invertible. It does have an inverse. Okay, so let's do example 5a. Okay, this is at the bottom of page 87. And by the way, you can go to larsonprecalculus.com and see an interactive version of this type of an example. Okay, so here's the graph of f of x is equal to x cubed minus 1. Now, remember what this is? This is a vertical shift downward from x cubed. X cubed would go through the origin. This goes through minus 1. It's a vertical shift downward. Okay? There's the graph. Now, guess what? You can draw all the horizontal lines you want to. You'll never intersect the graph more than once. Right down here, it looks like it might be tough. I can't get right down there. Where is my pen now? There it is. Right here. But still, if you blew this up, yep, it's still 1 to 1. Okay, f of x is a one-to-one function. It does have an inverse. We're not about to find the inverse yet. We'll do that later or something like this, but that does have an inverse. That is a one-to-one function. It passes the horizontal line test. Now the b part is this function here, x squared minus 1. It takes the squaring function that we had before, lowers it by 1. That's what it does here, vertical shift downward. And guess what? Not one-to-one. Look at that. That horizontal line intersects twice. Now, if you restricted your domain to be only from minus infinity to 0, yes, that would be one-to-one. Or if you restrict your domain to be 0 to positive infinity, yes, that would be one-to-one. You could take inverses then of those restricted domains, and that would be have an inverse on each side, but it would be limited. Okay. But the way it's written, x squared minus 1, all real numbers, nope, not one-to-one. Because it is possible to find a horizontal line, in fact, an infinite number of horizontal lines that intersect the graph at more than one point. F is not one-to-one, does not have an inverse over that entire domain. Okay. Now, that was example 5, bottom of the page. There is a checkpoint after 5. Please look at, do the checkpoints. Okay, now, whoa, 4 minutes to find inverse functions algebraically. Okay. Since we are running out of time, let me ask you a question. When we finish 1.9, which is just 2 pages, we're going to have the second test. Okay. Now, only a few of you have turned in the first test that I've gotten so far. I hate to pile another test on top of you, but I'll give you the option. If you're basically through or almost through with the first test, do you want me to go on and post the second test? Even though we haven't covered everything on it, you can at least get started on the first part. Or we'll wait till Tuesday when we finish this section, and then I'll post it then. Y'all have a preference? Say again? Okay, I'll go on and post the test. Now, it's probably going to be later today because I don't have any time between this class and the next one, but I'll post the second test. Now, the second test is almost twice as long as the first test was. The first page of it is going to be fairly similar to your first test, but the second page, and maybe some on the first page, is going to be the stuff we've covered since the first test. The first test only covered 1.4 to 1.6. This will cover 1.4 to 1.9. So the first half is a lot like the first test. Second half is going to be new. And it's a little heavier toward the second half too. All right. Finding inverse functions algebraically. For relatively simple functions like we did first, you can find the inverse functions by inspection. Most of the time that's not going to be the case. For more complicated functions like the ones we've had later, they gave us the inverses or said check them and see. That one, no way you could have done that. So here are the guidelines for finding the inverse. It says the key step in these guidelines is step 3. Now I don't number mine the same way they do. What they call step 3 is pretty. Interchanging the roles of x and y. That's where we started. That's what makes an inverse function. That step corresponds to the fact that inverse functions have ordered pairs with coordinates reversed. So here are the guidelines. I don't know if we're going to have time to do them all, but let's at least look at them. Okay. First thing you better do every time is use the horizontal line test to decide whether it has an inverse or not, which almost means graphing the function. Okay, that function f, make sure it has an inverse before you start spending time trying to find it. Okay, sometimes you can think through this, other times you actually have to graph. Okay, now once you've decided it does pass the horizontal line test, then in the equation f of x, what we said from the beginning, replace that f of x with y. Okay, good choice. Okay, now this is where I split this into 2 parts. Next step, flip the x's and y's. Interchange them. Next step, then solve for y. I don't know why they put this as one step. That's one step. Here's another step. Solve for y. Then, once you've solved for y, replace that y with f inverse. Just like you replace f inverse with y here, f with y here, replace y now with f inverse once you flipped them. Now, the next step is a long one. Verify their inverses. How do you do that? You have to show that f of f inverse is equal to x and f inverse of f is equal to x, which we've already done, but you know that does take a little bit of time. So those first few steps are pretty straightforward. This one may take a little bit of effort, but most of the time they're pretty straightforward. Okay? Now, we'll start next time with example 6. And I might need to go back and review those steps with you again, but we'll do that if necessary. Let me give you some homework exercises. We almost finished 1.9. You can do any of the odds, 7 through 13. They're all at Calc Chat. 9's at Calc View. Terrell must have gotten kicked out or had to leave and came back just in time to get your homework. Any of the odds on page 90, 1.9 exercises, and going further, 7 through 13, all at Calc Chat, 9's at Calc View. Either 15 or 17, both at Calc Chat, 17's at Calc View. Do number 19, it's at Calc Chat. Any of the odds, 21 to 31, they're all at Calc Chat, 23's at Calc View. 33's at Calc Chat, 35's at Calc Chat. 37 and 39 are at Calc Chat. 41 and 43 are at Calc Chat. 41's at Calc View. Okay, stop there, and then after that, after we do this next thing of finding them algebraically, we'll pick up with 45. Any questions? Okay. Hopefully, by next week, I will know if we'll have class next Thursday or not. For those who came in late, I met with my hematologist in a telemedicine video chat type thing, and I need to have another treatment coming up. He asked for more blood work, which I did yesterday. Hopefully he'll have the results by tomorrow, and he'll let me know what kind of treatment and when it'll be. There is a chance, a very good chance, it'll be a Thursday, Friday. Most of the time I schedule them on Friday, but this time he needs to do it on, if it's things work out the way he thinks it's going to be, it'll be a Thursday and Friday. If I get scheduled early on Thursday, it'll wipe out this class. If I get scheduled later on Thursday, it won't wipe out this class. Maybe, or not all of it anyway. It may be that they're all booked up next week and it'll be the following week, but sometime in the future, a Thursday class may or may not be affected. So just to let you know, watch out for that. If you aren't here on Tuesday, be sure you check and see if I've scheduled a Zoom meeting for you on Thursday. Okay, don't use Tuesday's Zoom to try to log in on Thursday if I haven't put one out on Thursday. That meant we can't meet. But I'll try to let you know Tuesday if I know. Any questions? Okay, I'm going to stop sharing. I'm sick and tired of sharing here. And unless there's some questions, we're going to end the meeting. Any questions? All right. Y'all take care. Have a good weekend, which means a safe weekend. And what is it? I might see one or two of you in physical science later today, but otherwise, I'll see y'all on Tuesday. Okay? Take care. Bye-bye.